Good morning. Even if you don't know Bjarke Ingels, which is unlikely if you're sitting here, you've probably seen his work. From 2 World Trade Center, the next amazing addition to New York's skyline, to Lego's amazing, crazy headquarters in Denmark, Danish architect, founder, and creative partner at BIG, which is the Bjarke Ingels Group, is one of the most exciting architects working today. And though you might know his visual stamp, you probably don't know how hard he's working to make sure that next generations actually can see the stuff he's built. By the time you walk into the lobby of 2 World Trade Center, you'll be protected by the Dry Line, the U-shaped raised park that Ingels has designed and is being built to protect Lower Manhattan from deadly storm surges. And if our great-grandchildren decide they want to leave this planet, they might find themselves living under Ingels' designs elsewhere, like on Mars. But I'm going to let him tell you about that. Your Excellencies, ladies and gentlemen, distinguished guests, I'm pleased to introduce Bjarke Ingels.
Your Excellencies, ladies and gentlemen, it's a pleasure to be here in Dubai. And before I begin leaving this planet, I'd like to talk a little bit about some of the ideas and sets of values that have informed our practice here on Earth. For instance, this idea of looking at our cities and buildings not as accumulations of facades or objects, but as man-made ecosystems where we channel not only the flow of people, but also the flow of resources to our cities and buildings. Our company is located in Copenhagen and New York. We're roughly 500 architects. As you can see, I have very committed colleagues. And it's actually quite important because when you're trying to do things differently, you're going to experience so much resistance that if you're not really passionate about what you're doing, you won't have the sort of energy or the resource to persevere. And then a little Danish lesson. The Danish word for design is formgivning, which literally means to give form to something that has not yet been given form. In a way, to give form to the future that we would like to live in. And just to give you some examples, we just finished this building in New York. It basically combines the social space of the courtyard together with the density of the skyscraper, creating what we've called a court scraper, and also really transforming the skyline of New York City. We did the home of the Lego brick, which is conceived as a man-made mountain of interconnected playgrounds that is as inviting and sort of interactive on the outside as it is on the inside. Also, it is probably one of the only museums in the world where you actually have to touch all the artifacts. We designed the Danish pavilion in Shanghai, looking at sustainable cities and trying to show how a sustainable city like Copenhagen, where half of the Copenhageners, they commute every day by bicycle. So we try to allow people to experience the thrill of riding the bike through the city instead of being stuck in a traffic jam. Also making it the perfect museum for impatient people, because you could do the whole museum in 5 minutes on a bicycle. We designed the Copenhagen Harbor Bath that extends public life into the water, showing that a clean harbor is not only good for the fish, it's also amazing for the citizens because you don't have to drive your car for hours to get to the beach. You can literally jump in the port. We're building this power plant. It's going to be the cleanest waste-to-energy power plant in the world. So clean that we've been able to turn the roof into a man-made ski slope, complete with hiking paths. So actually the power plant is going to be probably one of the most popular parks in Copenhagen. It's opening in October this year. We designed a series of buildings, for instance, the mountain in Copenhagen, that creates a hillside of homes with gardens by putting them on top of a parking structure. We created the 8 House, where you can literally walk and bicycle all the way to the penthouse, sort of extending the social space of the city up to the roof. And as a sort of a almost like 8 House upside down. In Amsterdam, we're doing a city block where you can sail into the courtyard itself, sort of combining the dry land and the water. Next month, we are opening the headquarters for the Shenzhen main energy company, where the facade is designed in such a way that when it's facing away from the sun, it's all glass. When it's facing the sun, it's almost entirely closed, roughly 50-50. And within this logic, you can make sort of specific openings, you can capture certain views, you can make sort of main entrances. But this idea alone reduces the energy consumption with 30%. So not only does it have an energy effect, it also has an aesthetic impact. In a similar way for Google, we're designing their headquarters, so the entire facade is made out of photovoltaics. So either we turn the photons into electricity, or we allow them to become daylight for the workstations. And for a similar amount of people in New York, we're creating a high-rise where every floor is connected to the floors below and the floors above, sort of connecting the entire sort of 80-story building in a sort of a social spiral from the ground to the sky. Here in Dubai, we hope to create the Hyperloop together with the Dubai Future Foundation, connecting Abu Dhabi and Dubai to start with in less than 15 minutes. And finally, in New York, after Hurricane Sandy came and wiped out most of Lower Manhattan, we're now designing a park that is not only going to be what protects the city from the next superstorm, but also will create a much more lively and engaging and accessible waterfront. So you can say all these projects are attempts by us to give form to the future that we would like to live in. And I think essentially that is what architecture is. It is the art and science of making our planet more habitable for life. And when you look at sort of how our the human presence on the planet has evolved, it has been shaped by primarily developments in technology and climate change. If we take sort of a 300,000 year history of man on planet Earth, it started with when we sort of learned to control fire. We could move north into colder climates. We could also cook new kinds of food. We then developed boats, so we could sail to Australia 65,000 years ago. Then global warming actually made the glaciers recede, and we could visit Europe for a while until the most recent ice age came back and pushed us more towards the east. Then the glaciers melted again 15,000 years ago, and when they melted, they also opened a land bridge connecting Siberia to the Americas. And when the glaciers finally disappeared, we could sort of occupy the rest of the planet. So just a sort of development in technology of movement, the Roman Empire was enabled by the Roman roads and horses. You could span the Mediterranean in 3 months by horse from Spain to the Middle East. 500 years ago, we could sail in 3 months from Spain to the New World. Then we developed the railroads like 150 to 100 years ago, allowing us to travel like 10,000 kilometers in 4 weeks. When we invented the airplane 60 years ago, we could get to Australia with a lot of stops in 2.5 days. Today we can do it in 16 hours. And if Elon Musk has anything to do with it, we can do it in 39 minutes with a rocket very soon. Almost 50 years ago, we traveled to the moon in 100 hours. And in 4 years, SpaceX promises that they can send us to Mars in just 3 months, which means that 500 years ago, Magellan's crew on their sort of circumnavigation of the globe, they traveled from Spain to Brazil in 3 months. We will, 500 years later, be able to navigate an ocean, not of water, but of space, and put our first boots on another planet, the first step in becoming a multiplanetary species, and eventually to sort of inhabiting and animating the entire solar system. So why begin with Mars? of course, it's our most immediate neighbor. It's sort of medium sized of the solid planets. It's roughly the same size with similar qualities to the moons of Jupiter and Saturn. But where the moons of Jupiter and Saturn are 2 to 4 years away, we can actually reach Mars in only 3 months. When you look at the temperatures, Venus and Mercury are like steaming hot. The outer planets are freezing cold. So Mars is somewhere, it's a little cold, but it's somewhere within the habitable range. You have 20 degrees Celsius at equator in the summer, which is roughly what we have here in the morning right now. When you look at gravity, just to give you some ideas, Earth, a person that weighs 100 kilos on Earth, would only weigh 38 kilos on Mars. So it's like the fastest diet you can get is to go to Mars. And by comparison, if you go to Jupiter, you'll weigh 1/4 of a ton. So it's going to be nice and light to hang out on Mars. And when you look at wind speeds, Mars actually has like fairly peaceful winds compared to Earth, and compared to the supersonic wind speeds you have in the outer planets. So when it comes to pressure, all of the outer planets, it's almost like walking at the bottom of the Mariana Trench. It's so dense, the atmosphere. The atmosphere on Mars is very light, which is a challenge. And then maybe one thing that is like an almost cosmic coincidence is that Earth obviously has a 24-hour day cycle. Mars has a 24-hour and 40-minute cycle. It's almost the same. It's even nice because we get 40 minutes extra, which I think everybody could use. And if you just compare it, for instance, like Mercury, a day is almost half a year. So it's quite unique that we're so close. And also the seasonal tilt of Earth and Mars is practically the same. And just to give you an idea how important that is, that means that we have the same seasons on Mars and Earth. Uranus has a tilt that is practically perpendicular to the sun, which means that if you're standing close to the North Pole on Uranus, you'll have 21 years of daylight followed by 21 years of night, which would make it like pretty insane to try to live there. And actually Mars, if you for instance compare like Mars and the Moon have like a lot of the same things, but most importantly Mars has both water and carbon, which are the 2 main ingredients in life. So we have all that ready available. Mars doesn't have a magnetic field, so therefore there's some radiation that we need to shelter us against. But when you sort of analyze the different planets and moons as a real estate project, you can see that Mars is a very valuable piece of real estate. It has almost half the radius or diameter of Earth. But even though it actually has this exact same amount of dry land because it doesn't have any oceans, so it's an amazing amount of space, the blue planet and the red planet. Actually, the Atacama Desert on Earth in Chile is the place on Earth that is the most similar to Mars. It even looks like Mars, except the sky. And then maybe one little interesting fact that I hope we can all enjoy soon is that where the sunset turns the sky red on Earth, because of the fine-grained dust in the atmosphere on Mars, the sunset actually turns blue, which is going to be sort of an amazing experience for future Earthlings on Mars. And then maybe like one last thing, here you see the amount of satellites on Earth. We actually have 14 satellites already flying around Mars. So that means that actually since the 60s, we've been visiting Mars quite frequently. So we have a lot of knowledge. We've looked at the planets, we've seen how the poles expand and contract. It's frozen CO2, so dry ice, but you also have frozen water in certain places. And we've seen the sort of the mountain ranges, the flows of lava, the sand dunes, the archipelago. There's no liquid water, but there was an ocean in the past, so you have these sort of remnants of islands. This is a dust devil, a dust storm on the surface of Mars, a landslide happening in front of our eyes. And with the different rovers moving around and Curiosity is still active, we have boots on the ground, or at least wheels, We've seen frost in the mornings on Mars. We've seen like fields of cracked dust. We've seen car tire tracks. So it almost looks ready and available to explore. So there's a lot of good things about Mars. We have a few challenges. There's too much radiation for humans. It's actually fine for plants, but it's too much for humans. There's very little pressure, rather cold temperatures, down to minus 150. There's no breathable air, and there's no readily available water, but it is there. Where could we land? It should probably be relatively close to the equator to have a good temperature and to be able to power ourselves with photovoltaics. These are some of the landing sites where we've already been, and these are some of the sites where we're looking at going. And here you can see the remnants of the ocean. The ocean floor has fewer craters because it was covered by water. It might be a good idea to go to some of the lower areas because you have denser air and warmer temperatures. This is the largest Grand Canyon, Valles Marineris. It's 4,000 kilometers long and 7 kilometers deep. It might be an interesting place because you can be sheltered from radiation with the rocks. But actually here on Earth, we humans have already become really good at surviving harsh climates. One example from Tunisia that at first glance looks like a lifeless desert. But when you move close, you realize that it's a densely populated human habitat. Houses have been excavated from the ground. The thermal mass and the shade of the earth provides a cool temperature. You have sort of protected and shaded outdoor spaces, uniform material, cozy interiors. So essentially using the planet to respond to the climate. In Arizona, in a similar way, what looks sort of uninhabited actually turns out to have these villages sheltered from the elements under the overhanging rocks, using the local materials, excavation and new build, and getting protection from the landscape. And finally, when you look at the Arctic, which somehow has more similar temperatures to Mars, you see this sort of Kangerlussuaq in Greenland, where the igloo was developed, this idea of the spherical form that provides maximum contained volume with a minimum of surface. The porosity of the ice actually creates insulation, more nomadic structures using membranes to trap heated air. And actually, the Eskimo or the Inuit taught Roald Amundsen, the Norwegian explorer, how to live in the Arctic region, teaching him how to eventually become the first man to reach the South Pole, because he didn't try to bring his Norwegian lifestyle, he tried to live like an Arctic resident. Robert Zubrin, the author of The Case for Mars, was inspired by this, saying that if we want to go to Mars, we have to live off the resources that are available there in the atmosphere and in the geology. So in a way, we have to become Martian. So what would a Martian vernacular architecture look like? First of all, it's going to be incredibly expensive to bring things to Mars. So of course, the first people that go there will have to bring their habitats, but then maybe we can bring the machines to use local materials to build our buildings, and then eventually we should bring nothing and just live off the land. Also, we're going to have to create our own little biosphere, a contained, self-contained ecosystem. And basically, a human needs 2 liters of water and a certain amount of nutrients. We are going to have to be able to grow our own plants in order to sustain this. So somehow we have to find ways of creating the living conditions for humans and the living conditions for plants in an intertwined ecosystem. So how do we create sort of a Martian man-made ecosystem? So basically what we do have is regolith, the local rocks. If we make a little sorting plant, we can actually get frozen ice, so we can get water. We can get basalt stones and local sands. With the water and the sand, we can create bricks. We can make Martian concrete and ceramics. The sand, we can also sort it, and we can get silicia, aluminum, and iron oxide. With that, we can make aluminum, and we can make glass, and we can make electronics and photovoltaics. With the photovoltaics, we can make electricity. And electricity and the water, we can make electrolysis, splitting the water molecules into hydrogen and oxygen. Combining that with the CO2 that is abundant in the atmosphere on Mars, we can use a Sabatier reactor to create methane together with the oxygen that becomes a perfect rocket propellant, so we can create a bridge between Mars and Earth. As a byproduct, we get carbon monoxide. We can use that with the iron oxide to create steel. We can use a chemical reaction with the water and the carbon monoxide to create hard plastics, fiberglass, and soft plastics. Of course, we have to recycle the materials we create constantly. We can make sort of transparent membranes to create inflatable environments. And of course, the water will allow us to make plants. We can create root zones and biotreatment to clean the water. We can then use water also for recreation, for aeroponics, aquaponics, hydroponics to create food. And finally, we have all of the ingredients to actually sustain life on Mars using exactly what is already there. In Western Europe, we have 150 square meters per person. On Mars, we should probably settle with a little bit less. There's too much radiation on Mars. 110 MSV, which is like twice of what we allow a radiologist to be exposed to. But then looking at human behavior, for instance, in North America and the United States, we only spend roughly 8% of our time outdoor. So if we say we only spend 18% of our time, and we sleep like a third of the time, 18% of the time above ground, then we can actually bring our radiation down to less than what we allow an airline crew member to receive. So it's quite tolerable. And of course, like rather than having like the Earth distinction between indoor and outdoor, we're going to have a lot more sort of different gradient. So almost like looking at these like vernacular examples from Earth, excavation, 3D printing, and inflatable membranes seem to be the tools. The inflatable membrane has the advantage that with very little material, we can create a pressurized environment, but it doesn't provide protection from radiation or meteors. With 3D printing, we can create more radiation protection and more meteor protection. And finally, with excavation, we can be fully protected, but we can't really get air tightness. So when you look at the three different techniques, none of them actually provide what we need. But when you combine them, we actually get a sort of an ideal human habitat on Mars. You can imagine different gradients of radiation protection, allowing you to sort of inhabit different parts of the environment at different times of the day. Of course, the spherical form is the most effective. It's also the one that we can sustain with a pressurized environment. So essentially imagine living inside a balloon with a mesh of Kevlar or carbon fiber. Inside this inflatable membrane, we can excavate, and with the excavated material, we can 3D print our habitats. Depending on the scale, different forms start making sense. In various typologies, and of course, as they get bigger and bigger, it could also be sort of tubular, interconnected, networked environments. So essentially, over time, we imagine an evolution of how we inhabit Mars. So the time scale for this is that the Dubai Future Foundation has said that in 100 years, or 99 years, in 2117, we're going to have an Emirates city on Mars. But we're going to start already now with the Mars Science Center as a prototype right here in Dubai, in the middle of Mushrif National Park, sort of well connected to the entire city, in an area where you actually have mostly sand to begin with. We want to create a prototype where you can experience how it's going to feel like living on Mars for education, research, exhibitions, and studies of biophilia. So basically, exhibitions that can sort of inspire future generations to want to sort of study to become the scientists that bring us to Mars. Collaborations with various companies, various knowledge institutions for research to develop the necessary technologies. Collaborations with different experiments in agriculture, ultra-efficient hydroponics, aeroponics, MIT's CD Farm, an obvious collaborator, and also to create a lovely environment like a campus, so that like living on Mars is not going to be like living inside a tin can. So we take this program, organize it with the architecture we imagine for Mars, with these sort of overlapping environments, permanent exhibitions, temporary exhibitions, university and research. We imagine activity gardens and exhibitions, farming where visitors can actually visit these farms, and then sort of research facilities indoor and outdoor for the resident scientists. And basically, we want to build it right now and the next a couple of years using those techniques. So like building inside the protected area of the dome, protected from the elements, using 3D printing, using the existing available sands that actually almost look Martian in their color. Also, when you're 3D printing, curvilinear language actually becomes more resource efficient. So the architecture on Mars is going to have its own style, its own sort of granular texture, the rounded corners as a sort of Martian vernacular. Another interesting thing is the best shield against radiation is actually hydrogen. So imagine 1 meter of water protects as much as 8 meters of rock. So you could actually imagine these skylights with water that actually protects you fully from the radiation actually making sense on Mars. So here you see the sort of the lobby from where you can go and explore the exhibits, always in this sort of garden-like feeling, because you really want to have as much biophilia as possible. You can visit the farms, you can visit the labs, and sort of explore this sort of human exploration of Mars. Finally, Dubai has a very different climate than Mars, so of course we have to adapt the architecture in certain ways. Thermal exposure becomes a major issue. So on Mars, we're going to use geothermal to heat. In Dubai, we're going to use it to cool the environments, and we're going to sort of manipulate the membranes to actually filter light, so that the same membrane can both sort of function as a greenhouse, but also as a darkened auditorium. So maybe just to conclude, why is this relevant for us on Earth? Basically, we believe that a lot of the challenges we have today on Earth can actually be answered by the technologies that would allow us to live on Mars. And just quickly looking at some of the United Nations Sustainable Development Goals, for instance, like efficient farming on Mars, we will be 10 times more efficient, or will have to be, than we are currently on Earth. On Earth, we have billions of cubic meters of water. On Mars, we only have 5 million cubic meters, so we need incredible efficiencies. On Earth, 2/3 of our energy is combustion. On Mars, we have no fossil fuels, and we have no oxygen to waste on burning. So basically, the idea of the sort of man-made ecosystems, the local self-supportedness, innovation in methods of transportation, and experiments in climates are all what's going to enable us to be successful on this planet. So if you imagine to finish off in the next 2 centuries by sort of slowly turning Mars from red planet into a green planet into a blue planet, imagine that what it takes to turn Mars into an entire man-made ecosystem is also what's going to make us the most capable custodians of the planet we inhabit today. And like Al Gore said, the first time we saw Earth from the moon, it made us aware of how much we actually have to take care of the home we inhabit today. And as a final thought, imagine in a couple of decades, our children or grandchildren looking up at the Martian sky, they'll see a sort of a reminder of their blue origin by this little blue speck seen from the surface of Mars, which is actually Earth, but looking at it from the planet that we now consider as home. So the first step in this is going to be the Mars Science Center that we're going to start building right here in Dubai in the next couple of years. Thank you.